All right, so after having had some general understanding about finding the confidence interval for a population proportion through the general lecture giving understandings about how to find a confidence interval in general, we are now ready to do an actual example where I should be able to put in detailed explanation throughout each step. So in what we're doing in this example, we are going to find a confidence interval to estimate the value of a p, a lowercase p, which is a population proportion value. And now we are going to start by looking at the following example. So let's have some time reading through the description of our example here. But so, according to the data from Washington State Department of Health on July 26, 2020, 4,633 COVID-19 tests were taken, and among those test results, 306 were positive. So now find a 90% confidence interval to estimate the statewide proportion, or in common term, the percentage or the percent of COVID-19 positive of the same day. So here, looking into the question, I first have to make clear that a lot of time, commonly, any confidence interval problem will eventually have a statement somewhere in a problem asking us either to find or to construct. So right here, find a confidence interval. And the purpose of this confidence interval is to estimate the statewide proportion of COVID-19 positive on the same day. And looking a little further into this statement, so our main goal is to find the confidence interval. But this number given here is regarded as the confidence level. So I'm going to turn over to my writing board and let's get started nailing down a few given information here. So according to the description of the data, as far as given information, then what we have here is a confidence. We are asked to find a confidence interval, but what we have here is so-called a confidence level. And that confidence level right there is being a 90%. And this 90% right here, very commonly that's how it's written in any of the confidence interval problem. But when we're actually using that for doing the work, the computations, or any kind of computations, then we're going to need to put that in decimal. So 90% in decimal is a 0.9. So once again, to clarify that this 90% here being a confidence level, it's listed as a given one piece of given information. And so now let's look even a little further. So according to, I'm going to roll back to the beginning of our description of the problem. And according to the data from Washington State Department of Health on July 26, 2020, so 4,633 COVID-19 tests were taken. So this information, this piece of information right here, we can regard to that as we have a sample. So what we have now is we're given some information about a taken sample. So think about the test, or and let's pretend here that all these tests here are randomly taken. But what we have here, the number of tests there is being a sample, where our sample size here is being 4,633 tests. And so now the further information set among those test results. So of course, after we did testing, then results come back in a couple of days. And so among those tests, 306 were positive. So what I have here is actually bringing in for us a proportion. So 306 divided by 4,633. 33. And so this here gives us already a proportion. And in 4 decimal places, it's 0.0660. And in that way, this is about 6.6%. But so this proportion that we found, I have to make clear, it is not, what we have here is not the statewide, because remember that it's not the statewide proportion. It's a proportion, but it's just not the statewide proportion, because the entire state of Washington has a lot more residents, but the number of tests on that day, we only test 4,633 residents. And so this is not the statewide proportion. However, this is, in our understanding by far, then this is a sample proportion. And that is a lowercase p hat. And so, really, that's everything we have as far as given information. Confidence level being 0.9 or 90%. We use a sample that's out of 4,633 residents being tested. We found a proportion of COVID-19 positive being 306 out of 4,633 test results. And that came up to a proportion of being 6.6%. But this is only a sample proportion. And so now the idea is, and if we're looking back at the problem one more time, we want to find a 90% confidence interval to estimate. So this statement now is, let's get started going further into this statement. We want to estimate the statewide proportion, because at this point, and on any day when we're receiving test result from the state of, from the department, from the health department, then we will actually never know. We will actually never know the real proportion. And allow me to also further clarify that whatever we're studying here is only applicable to that day, that date being July the 26th, 2020, because of course it's COVID-19 is the disease, so it's spreading more widely and more widely. So every day this proportion of COVID-19 positive is different every day. But say on that particular day, let's see how we can rely on this sample proportion that we found about the COVID-19 positives to make some inference, to make some estimates about the unknown proportion here. So once again, this value that we're trying to estimate is only giving us a picture that reflects what's going on in that current day. All right, now on the line of numbers here that shows the p hat and p at some difference. Let's recall for ourselves the understanding about the confidence interval from the general lecture. So from what we previously learned, the interval is made centered at p hat. So from where our p hat is, that we really know the value, and we treat that as a midpoint of our interval, of our designated interval that we're looking for. The low is here, the high is here, and then that space between the sample value to either end of our interval is called the margin of error. And so in the way how it's looked, then that means the high, this particular spot right here being the high end of our interval. In the way how the picture looked, then mathematically it's from where p hat value, but we add with margin of error. And then same way, this low end right here is going to be the same as from where our p hat, I'm talking about numerically as a value on the line of numbers. Then this low end of our interval will be from where p hat that we currently know minus the margin of error that we will be able to find out. And so in that way, the confidence interval, so CI is my shorthand notation for confidence interval, but any confidence interval will look like the following. Low end is p hat minus the margin of error, and high end is from where p hat plus margin of error. And the in traditional format, low end comma high end inside a pair of parentheses, that is an interval. But among the statisticians, then a more common way of expressing the interval is, and you can see that this p hat, our current sample proportion value is exactly in the middle. So the confidence interval can also be expressed in a different form, and this form I'm about to write is more commonly used among the statisticians here. But the interval can also be expressed as p hat plus and minus the margin of error. So these are two different ways of how we can find our confidence interval. And so everything just now was a brief review of what we've learned from the general lecture about how to find a confidence interval. All right, so in that way, now we are completely ready to nail down our first confidence interval over here. So from where our known sample proportion, 0.0660, I am going to simply need to plus and subtract, add and subtract some margin of error. And that will create for me my confidence interval as the ultimate goal right here. So all we need to wait for, or we are waiting for now, is a formula to calculate margin of error. So the margin of error is calculated in by using the following formula. Margin of error equals from where our current p hat value is, which is known, we are going to multiply with 1 minus p hat. And then after that product, we are going to divide by capital N, the sample size. And remind yourself, all of these values are given and previously listed here on my left-hand side of the board. And once we have done that setup right here, that computation, that once we finish with that quotient, then we're going to put all that value inside the square root. And so notice how I'm writing all the operations here in a certain order. So we multiply first, multiply these two expressions, then we divide, and the overall quotient is being taken the square root after. And after the square root, we are going to multiply all that expression by a value that I call a z sub c right here. Okay, so right now it's just a formula that I introduced. Let's see how ready we are for using this formula. So in this formula, then except the z sub c value, which I will eventually discuss, then everything inside the square root expression here is already given. So what we're looking at here is 0.066, and I don't think we need to write that ending 0 there in the fourth decimal. Multiply with 1 minus 0.066, and we are doing the dividing by our sample size being 4633. And so all of a sudden we realize that we've had a lot ready for this formula already. So the only mysterious thing that's waiting for us right now is this value of the z sub c. All right, so let me now introduce how to find z sub c as a crucial part of our margin of error formula. So how to find the z sub c value. So first, our confidence level being 0.9. And so now officially I am going to give a symbol lowercase letter c to indicate that our confidence level given previously 0.9. And so the first step here is from where our confidence level is, I am going to perform the following math. 0.5 plus half of 0.9. And so 0.5 is by itself, but add half of 0.9 and remind yourself that 0.9 here is the confidence level. And so this value comes out to be 0.95 in its complete precision. And so this 0.95 right here is being referred to as the area left, or some left area. And then our next step, I am to find and see. The reason why I refer to this value as an area left is because in my next step, the plan is think about on the standard normal distribution. So this is the bell curve of our z-score. Okay. Then which z-score is it giving me an area shaded to the left to be 0.95, and that's the plan. So that's why this value coming out from 0.5 plus 0.9/2 equals 0.95 is being referred to as area left, because once we've had that amount, then we are going to look for, hey, if this 0.95 is being regarded as an area to the left of a z-score, then what z-score is it? And so you have done all of these problems back in your days learning about the standard normal distribution. So the only way to find this z-score is to run the INVZ value, to run the INVZ program, or some equivalent program, or some equivalent technologies over the web that allows you to go from an area to the left of a z-score. So here the designated area to the left of our z-score, of our unknown z-score, is being 0.95. So what z-score is that? That's what we're finding out. And so here again, allow me to demonstrate how I use my INVZ program, but that's a Microsoft Excel file. If any one of the viewer here is my students from statistics courses at different colleges, then you have this program uploaded on the class website, and feel free to download it and use. But it's a Microsoft Excel file, and once you open it, there are many tabs here, and specifically to look for the INVZ program, it is just the tab here that labels INVZ. But so once you open the program itself, the box on the left hand side is to indicate the left area, and this is the value where you can change, you can freely change, and then leave this box unchanged so that it can do the calculation. It can just show the final calculation result for you. So once again, a little bit back to the writing board, but so our left area here is being 0.95. We already know the left area. We want to find out what z-score that is. So for the INVZ program, I am going to enter 0.95 and hit enter. So the box to the left, to the right hand side here is going to immediately generate a value 1.64485,363. Now for anyone using a TI-83 or 84 calculator, the equivalent command to do the similar task is called the INVNorm command. And to get there, we go second variables, which will bring up all of the distribution functions for statistics. And now the command is INVNorm. And we hit enter. Now for the TI-83 or some earlier TI-84 calculators, after selecting INVNorm from our distribution menu here, instead of seeing the menu as you have seen earlier, you will see simply just the command being printed right on your home screen as indicated here. And now we're just going to enter 0.95, which is the amount of area to the left of our designated z sub c value. So 0.95 is here. Now we're going to hit enter and keep this mu value at 0, keep the sigma value at 1, and hit enter a few more times. And just like that, for TI-83 users or earlier TI-84 calculator users, then we have to manually type in these three values separated by commas as indicated here. And so now we're just going to simply hit enter one more time to come up with a final value. And this value here exactly agrees with the value which came out from my INVZ program written on the Microsoft Excel. But this value right here is going to be our, so once again back on my writing board, and usually for this kind of problem, even though you need to be aware that in every different assignment problem that you're doing about the rounding, but usually throughout lecture I use, after INVZ program, I use a final answer of being 3 decimals. So here 1.645 here. And so this is my z-score, the z-score close enough to give this area to the left, the z-score, the close enough estimate of our z-score such that satisfying the amount of area to the left being 0.95. But so it's a z-score. But the entire reason that led us to find this z-score because we start out with our confidence level. So with our confidence level, it consequently led to, with our confidence level being 0.9, it consequently led us to 0.5 plus 0.9 over 2, and to have this area left. And so you can now sense that this z-score is relative to this given confidence level. And that's the reason why we refer to this as a z sub c. Right here it's a z-score but specifically designated for this, equivalent to this confidence level. And so that's how we find z sub c. And the 2 steps here are being the critical steps. And so now just brief reminder, good thing is that finding z sub c can always stay in the same set of instruction. So to find z sub c in general, all you need to do is a big step 1, 0.5 plus your current given confidence level over 2. And this amount here is being referred as area left. Then once we've had area left, then to find z sub c, the work can be easily done by running the INVZ program or any kind of equivalent technologies over the web that serve similar purpose. But here I'm going to run INVZ on the amount of area left from step 1. That's it. So now I am finally ready to make a final computation value. Z sub c now is found out to be 1.645, and I am going to multiply all that with the square root expression. And so all it is now is for any of you who is viewing this and doing work at the same time, which is what I highly recommend it. Then make sure you follow the order of operations carefully. That's all. Okay, so after successfully filling in all the values, now our final answer to this in 4 decimals, which is what I normally use. All right, so calculation comes out to be 0.0060. So that is the margin of error that we have found. And our final confidence interval here, so I can just make note again, but final confidence interval is now from where our known sample proportion value, 0.066, and at 90% level of confidence. The statewide COVID-19 positive on July 26, 2020 is only 0.006 up and down from where our sample proportion was. And that is how we find a confidence interval. And in traditional interval format showing low and high, then the low is can simply be found by subtracting this margin of error from our sample point, from our sample value. So 0.06 is our low end, and the high end will come out by simply adding this margin of error to the sample value in the middle. So our low end will come out consequently to be 0.072. So it depends on how any of the viewers' comfortability with reading intervals. But if this format here is more comfortable for anyone viewing the video, then you can think of this as, so if according to our sample on that day, July 26, 2020, if this sample proportion was a 6.6%, then statewide proportion of COVID-19 positive on that day was anywhere from 6%, that's the low, to 7.2% among the Washington residents. That's one way to understand it. Or another way to understand that's quite common to the statisticians is that the statewide proportion of COVID-19 positive on July 26, 2020 was anywhere 0.06 up and down from where 0.066 was.